Now we'll start the second part of the introduction, lecture 1, and let's move on. Now we're going to look at the second example from World War II of how radar made a big difference. And it has to do with the first cruise missiles that were ever developed in the world, called the V-1, or buzz bombs. Here's a picture of the buzz bomb. Let's look at what the threat was from this. It was an unmanned cruise missile. Its propulsion system was a ramjet located here in the back. It was guided by a gyro compass autopilot. It could go had a range of 250 kilometers, and it had about a ton of high explosive warhead. And the Germans launched about 9,000 of these in the 40s, in the mid to the late 40s. Excuse me, I was thinking the mid to late part of the war. The latter part of World War II, and about 2,400 of them impacted the London area. A great number of them were shot down. Initially, of course, they fly at about 400 miles an hour, which is pretty fast, but they fly a very straight line at a relatively low altitude of 2,000 to 3,000 feet. And the question was, how do you knock these things down regularly and easily when they're pretty fast? And it's hard. And there were difficulties in that. And I want to point out how radar got the kill rate up to just about 1, very close to 1. And there's a set of radar technologies that were involved in that. The first of these was the radar I talked a little bit earlier about, called the SCR 584. It has a 10 centimeter wavelength, that's a couple of inches like that, and about 4 inches, 3,000 megahertz. It had a magnetron for power, which generated 250 kilowatts of peak power, and a pulse. It would send a pulse out that was a little less than a microsecond in length, and it would send out a burst of pulses a little less than 2,000 in a second. This antenna is a little less than 6 feet in diameter, and it had a 4-degree beam width. And its azimuth coverage was 360 degrees because this antenna could rotate in azimuth and in elevation. It had a maximum detection range on an aircraft of about 40 miles, and a range accuracy of 75 feet, and a remarkable angular accuracy of 6/100ths of a degree. Okay, so it's a very accurate radar system in terms of being able to see 360 degrees, and then when the operator saw a target of interest, to lock onto that aircraft and follow it very, very, very carefully. Okay? Now, here's a picture 40 years after the radiation laboratory, at its anniversary of the SCR 584, with a couple of the gentlemen. Notice the white beards, and the white beard from Leo Sullivan, and the white hair. Leo was in his 20s. He was a young guy. He was like the young guy. And Leo got sent to the war to test it and to help get it operating. And I'll get into that story. He has a wonderful oral biography that is one can access on the IEEE website. If you just said Leo Sullivan, IEEE, and you Googled that, and you said SCR-584, you would get Leo's 40 or 50 page oral autobiography biography that you could access and read of his remnants. Leo has since passed away about 5-6 years ago, and he was just a fine gentleman. He was a group leader at Lincoln Laboratory when I was in my late 20s, and so I got to know Leo, just a great guy. But the heroics that what those guys did over in World War II, in the air defense, I'll get into in a minute. And anyway, you can see the parameters of this radar. It's the same as were on the previous view graph, but they got, for the 40th anniversary, they actually got this radar up and running from the museum, and they actually were tracking aircraft with it. 40 years later, the guys went back to the console, you know, forget these things after a while. And the excerpts from the reunion of the, Leo wasn't the only person, there were about 7 or 8 people who worked in the development who were at this was taken at Millstone Hill in Westford, Massachusetts, a research facility of MIT's Lincoln Laboratory, and again, courtesy of the laboratory for this photograph, for its use. They all had a grand time, and it was movies, videos, all of their remembrances were incorporated in a public broadcasting system, NOVA. And I think it was something like the invention that changed the world, or how radar helped World War II, or whatever. And it was many years old. You can probably get it from your library if you do a search. You can get it's certainly not on a DVD. You can get it on a VCR. It's a really interesting tape where the guys talk about some of their exploits. But okay, now we move on to the second triad of the 3 instruments that were part of the air defense system that knocked the daylights out of the V1. The second was the radar proximity fuse. Here we have a photograph, courtesy of yours truly, and here is an actual 1980s version of a radar proximity fuse. And there's a dielectric warhead that holds the antenna, and they operate at around 200 megahertz. They use Doppler frequency shift of the radar signal that's emitted out to detect the moving target, and when a threshold is crossed, the fuse is detonated, and that allows physical destruction without hitting the target. And that is a crucial thing. You don't have to be able to have this when it's hooked on to an explosive charge, be it an anti-aircraft missile or an artillery shell, to explode it and knock down the aircraft, or the V1 in this case. But you can just get close enough for the kill. And in many cases, 5, 10, 15 feet would be plenty for and then you'd get close enough and you'd knock it out. Here's a cross-section that I got from the web of an artillery shell, a proximity fuse of about the mid-1940s. And they all look, it turns out, there's miniaturization, but the point is they have to operate under very, very high acceleration as the anti-aircraft shell or an artillery shell is shot out of the barrel, enormous accelerations, and they have to have a radar that will work that well. And during World War II, Johns Hopkins Applied Physics Laboratory just broke the ground, and they made this kind of the V53 proximity fuse work like a charm. So when it got close to the V1, it would wipe it out. The shards from the shell would destroy the V1. So you've got a weapon that can kill it. You've got a sensor that can find it and track it. And what else do you need? Well, you need this device in the middle. And here's a block diagram of the whole system. This was developed by Bell Labs, and it's actually an analog computer. It would take the data from the SCR 584 of where the target was at a given moment in time, project ahead where it would be if at a slight time later an anti-aircraft gun, either the US's 90 millimeter or the British's 3.7 inch anti-aircraft gun, fired, and it takes time for that shell to reach that predicted point of the aircraft as it moved while the shell was going up towards it, and it would send direction information to the anti-aircraft guns to tell them exactly where to point and to fire, so that when the shell, there'd be an intersection of the shell and the aircraft. And when the SCR 584s were first sent, and obviously very quickly to Great Britain, they were set up all on the coast of Great Britain, the lower coast. They wanted to get those V1s before they could get to London and do devastation on the civilian population. They were indeed a weapon of mass terror. And the British had a kill rate without the radar, and with the British aircraft knocking them down, that was reasonable, but it wasn't as good as you could make it. And when Leo Sullivan arrived, and they realized that the operators, who were just getting used to it, didn't understand the manuals. So in his autobiography, Leo says they got a hold of a Red Cross ambulance, blacked out the white cross on the ambulance, filled it full of manuals on the SCR 584, and went from radar battery to radar battery, or I should say air defense system. They were locally isolated for their area of coverage, teaching the operators how to operate the system, operate all three components as a system. And immediately after a very short time, they get the guys up and operating, and boom, they were just getting them right and left. So they went one after the other, working day and night, until they got everyone all tuned up and running, and they got the rate up very close to 100%, very close to 100% by the end. By the time the V1 launching sites were overrun by the troops that had invaded in Normandy. It was like the stats are in Leo's book. It's like a 97 out of 104 over a certain period. They got so it really made a difference in that air defense system. Also, at the same time, roughly, another one of the operators from the Rad Lab, another young guy, went over to the Anzio beachhead in Italy, where the Germans operated the high ground. They had a lot of artillery, but they're also bombing the troops on the beachhead, which they couldn't get off of, every night. And he rushed over. They were using a radar system. I think it was the SCR 268, which the Germans knew how to jam. They knew what frequency it was on, and they could jam it and make it inoperative. So they brought the SCR 584s over. They dug them into the ground so that only the antenna was above ground. And the first night, and these operators finally knew how to operate the system, and they hooked it up with 90 millimeter AAA and the M9. And the Germans have been sending over, a dozen or more bombers each night when it wasn't easy to shoot them down. And the first night, they sent over 12 bombers. And the system knocked down 7 of the 12. Well, no pilots are going to fly when they lose that kind of aircraft. So a week later, they sent one more bomber over at night. It got knocked down, and they just didn't send any more bombers over. It's that kind of efficacy that this system had, and really, it's a neat, tells you. Now, I'd like to go over the radar basics. What are the positive and negative aspects of radar, what attributes it measures, and the block diagram of the radar system. We'll move on. Okay. The good things about radar is it's about the only sensor that can look way out and give you good long-range detection of targets and track them at thousands of miles. Today's radars. They can see very far and see over wide solid angle, very wide. And they'll operate pretty much in all weather and day and night. And you got to look pretty hard to find something else that comes even close in sensor technology. They've got that wide area surveillance capability. And since we're dealing with transmitter systems today that are coherent in operation, and that is from group of pulses to group of pulses, they're coherent. You don't lose the phase information. It doesn't become scrambled between one group of pulses and another group of pulses. We can use that property, and we'll go into it in great technical detail later on in several lectures. We can simultaneously detect targets really well, and we can reject unwanted targets that you see, what we call clutter. Unwanted backscatter from the ground, unwanted backscatter from rain, from things like chaff, aluminum that's dropped from airplanes. That was developed during World War II as a way to confuse radars. From the sea, birds, when they're in close, appear to be big targets, and I'll explain why later. Or if your target is very small and the birds are very small, you've got problems. But anyway, because of this coherence, you can also image targets, both fixed and moving. Fixed with so-called synthetic aperture radar techniques, and moving targets using the Doppler principle, which I'll explain in a couple of view graphs. And we're going to show you that this coherence allows us to take a line of sources of electromagnetic energy and phase that energy such that you can point the beam electronically by changing the phase of the different transmitters along a line. If you can change that phase very fast, you can point the beam over here and then microseconds later point the beam in another direction. You don't have to move a big antenna, some of which I'm going to show you are hundreds of feet in diameter. So you don't have that mechanical inertia to point the antenna in different directions. You can electronically scan the beam in microseconds. And you also have the ability to adaptively change the shape of the beam so that you can mitigate interference and people jamming the radars with unwanted extraneous noise. And the other great thing about radar relative to other media is that it's relatively lossless, and you've got relatively straight line propagation at microwave frequencies. And you'll see when we talk about propagation and what we mean by relatively. There are some media that are just hard to work with, like sonar. And actually, this relatively refers to a microwave at frequencies down in the 10 to 30 megahertz region. When you send a beam up, it hits the ionosphere and bounces back, and the losses you get in the ionosphere can be huge. But at microwave frequencies, you've got these good things. There's no free lunch in the world. That when you come with those positives, you're going to get that long-range detection, very far range. You need big antennas, big structural objects that are heavy, and you want a lot of power. Antenna size and power will give you that range. We'll see later when we discuss things quantitatively. And we use a lot of electrical power to generate the microwave power. And these big radars that really see out thousands of miles cost a lot of money. And some radars don't. Police radars, $1,000 or something. A radar you put on your sailboat or your power cruisers, a few $1,000s. But if you're going to want to see aircraft long distances away, you got to pay some bucks to do it. That's like a 5-star restaurant. If you really want to reach out, you've got to pay the bucks. You don't get a McDonald's price for a prime rib. And the radar beams do not propagate well through the earth. You can't see into the earth, into water, and it's hard to get them to go into foliage. At frequencies the order of 100 megahertz, they'll go down into the canopy of trees. And they don't see around corners, around obstacles like through a building. You can't see through buildings easy. A steel, you can't see through a building, through a mountain. They're vulnerable to jamming and anti-radiation missiles. You're emitting radiation. Someone can put some antennas up and say, aha, where the signal's big, that's where the radar is, and you can home in with an anti-radiation missile. And the target can detect that's being illuminated. So if something, you can see it, it can know where you are. And it can locate the target in angle space. You can locate the radar in angle space by listening and having a couple of antennas set up. Now the echo from some targets can get very small. Anyone who reads the newspapers can just Google stealth, low observable technology, B-2, F-117, And you can read about that, and that's a difficulty for radars. And but of course, because of the sensitivity, we won't be getting into that. Here are some pictures of different radars highlighting what they're used for. Here are some surveillance and fire control radars. Obviously, the word surveillance says it looks over a big amount of space, and it can tell me anywhere in that giant amount of space, solid angle, angular space, and range where things are. And it also can do fire control. That is, it can direct fighters or missiles to where the object is. That SCR 584 was both a surveillance and a fire control radar. And these radars are big, hundreds of feet. These are electronically scanned phased arrays. This is an electronically scanned phased array that's used to track and surveillance and for missiles. Inside of this big radome out on the island of Kwajalein is another system protecting the fleet on 4 sides of the destroyers and cruisers that protect each battle group are phased array radars. This is the Arleigh Burke class of destroyer, and here are 2 of its phased array radars. Each one looks at plus or minus 45 degrees, so 4 of them cover all 360 degrees. And here is a ship-based antenna that is used on a lot of destroyers and on some aircraft carriers to detect aircraft that are up in this nearby the fleet. Now we move on to airborne radars. You've always got the Earth is curved. You know, we learned that, and since it's curved, you can't see out forever. You got to get up high to see far away. And if you're on a ship, you've got a certain horizon. We'll get into the equations of how you figure out what your horizon is. And so for an aircraft carrier and its battle group, it wants to have some radar eyes above the fleet so it can see out a couple of 100 miles at least, and so it uses this E2C. This is a rotating antenna on that E2C that goes above the fleet and looks around and sees things that you couldn't see with a radar on the ship. You've all heard of the AWACS radar, probably. This is a picture of the antenna, which is inside that radome, and it has a 10-centimeter wavelength. And here is another this is if you look inside of this, it looks like an a command and control center, but really underneath the command and control center is where the transmitter is, and here's the antenna. You see it is there too, but it does surveillance, fire control, and command and control high up for the Air Force. And also for ground surveillance, the Air Force has the Joint STARS system, which was used in the Gulf Wars, both of them. And it has in this radome underneath this antenna. Here's a picture of the antenna when it's on the ground and the radome's opened up. An X-band radar that can see pictures on it can tell you the battlefield in a significant area. And a couple of the pictures have been released, just 2 that I could find in the public media or on the web and the public domain. And also we have in fighter aircraft, when they want to knock down other fighter aircraft or bombers, they want to look out far away and fire missiles at the aircraft that are out there, bring them and see what's there, see where the enemy is, and go after them. And airborne radars are located, let me go back, in the nose. And this is a planar array on this jet aircraft, and here is a more complex phased array inside the nose of another jet aircraft that can do not only, this has got a multi-mission mode, not only do surveillance and tracking, fire control, but it can also look on the ground and do things such as synthetic aperture radar, map the ground, and look at moving targets on the ground that it can do battle with. And in unmanned air vehicles, like Global Hawk here. Radars are placed to give battlefield awareness to unmanned aircraft so that they can see where the bad guys are and take care of them. Now, radars aren't only used on those tactical missions, but a great many radars, huge ones, are used, so-called instrumentation radars. They're like the referees, the scorekeepers. If you want to test out something, action that's going on in the sky, like a missile defense test, or you want to fire, have a fighter aircraft fire a air-to-air missile at a drone and see how well it performs. You want to use a radar like this multiple object tracking radar that the Army has built, that Lockheed Martin built for the Army, and it's used at a lot of test ranges. Here are a bunch of radars at these four that are located out on the Kwajalein Atoll in the Pacific that are used as scorekeepers and data gatherers for missile defense tests. They give you an idea how the frequency range they operate on. This operates UHF and VHF frequencies. That's from 400 megahertz to from say 0.4 meters to 2 meters on two different frequencies it operates. And then this radar, the radar inside this radome, has a wavelength of a millimeter, 35 and 95 gigahertz at two frequencies. It's a dual band. This radar inside this radome operates at 5 centimeters, and this is TradeX, it operates at a S band and L band, 10 centimeters and 23 centimeters. This guy here is so big that it's I think it's 120 feet across, and when it rotates in azimuth, there's a set of railroad tracks down here. Okay, and I'll show you later the picture of a human being, a man, who's up on a little galley next to this antenna. I'll give you an idea of the size of it in the antenna lecture. These are big instrumentation radars. Okay, radars are also used extensively in the civilian world. Here are two photographs of the mainstays of our air traffic control system, the so-called airport surveillance radars. This is an ASR-9. I believe this is located, this one located in Boston, and also the ARSR-4. These were built. This one was built by Northrop Grumman. This one also was built by Northrop Grumman, although the picture is courtesy of Lincoln Lab. Here's a real serious-looking military policeman with a speed radar measuring speed. And also on top of air traffic control towers, you might have noticed a pancake-shaped radome. This is an ARSR-4. Excuse me, an ASD-4, Airport Surface Detection Radar Model 4. And the ASD-4 looks at targets that are moving slowly near the surface of an airport, so you can see that aircraft on the runways aren't going to collide one with another. And then the Weather Service, NOAA, and the FAA operate a series of radars that are used for different important functions. There's the Terminal Doppler Weather Radar that looks near its position at a significant number of airports where there's a lot of turbulence. And microbursts can occur that have caused deadly accidents, tragic accidents, where planes coming and taking off have crashed into the ground from a sudden change in the vertical wind velocity. And this radar is used to detect those microbursts, automatically tell the air traffic controllers and vector pilots away from landing or taking off from those runways when those events occur. And then also the NOAA has a huge, vast complex of weather detection radars. Goes by two acronyms, WSR-88 and NextRad. And those radars, and we'll see pictures of them, the data from them, they're used to measure weather fronts and dangerous weather fronts that are coming, and give your weather. If you're looking a lot of the time at your local weather forecaster, these radars. So there's a lot of civilian uses, and even more. NASA uses them to track its missiles and space missions when they're taking off. NASA built this ground penetration radar to understand what's below the surface of the ground, use it on a extraterrestrial body or whatever. And here is a ground penetration radar. Archaeologists use these a lot to look for where interesting sites might be. And you can see an operator here and a person moving the ground penetration radar to see. They don't see very deep, but they see deep enough that you could see a buried body or artifacts for an archaeological dig. Radar was used by the Magellan spacecraft to map Venus. The synthetic aperture radar was built out at Jet Propulsion Laboratory. And lastly, you can't go by a civilian, dock where there are lots of powerboats and sailboats, and you don't see radars that detect the buoys that are located coming and going out of harbors, so that mariners in fog and at night can tell where they are safely, along with GPS is now very helpful. Okay, so now what is it that radars measure? We're going to look at that next. Let's first look at what the pulse of a radar looks like, and the pulse set of pulses. And I want to develop some definitions for you. Radar, like every other technology, has its jargon, its acronyms, its sets of short words, or whatever it is, BFF, best friends forever, and you got to learn these things. They're the language of radar, and I want you to know what they mean. So we're going to go over them once quickly. The peak power is the peak power within a pulse, and I want to remind you that this is the envelope of power that is transmitted. Within this pulse width is a complex sine wave of electromagnetic energy, and it's oscillating up and down at some frequency. But the peak power is power versus time. The peak power is that biggest value it gets to, and the width is called the pulse width. And then sometime later you get an echo back, it's the target return, and a little while later you'll send out another pulse. And what we call the PRI, the pulse repetition interval, is the time between those two pulses. And usually there'll be a set of pulses. There could be just two. There could be 20, 32, 64, 1,000. Whatever it is, that's the PRI of that radar with that waveform. The duty cycle is a measure of, in an average sense, of what's the average that the average amount that you're turned on and you're turned off. So it's the pulse width divided by the pulse repetition interval is the duty cycle. And it says on average the transmitter is turned on that fraction of the time. And that's the average power, would be the peak power times the duty cycle. Then the other quantity is the pulse repetition frequency, which is 1 over the pulse repetition interval. So for a radar that's continuously transmitting, its pulse length is just on and on and on, it's 100% duty cycle. It's always on. And just to give you an idea, not for every radar, and these vary over orders of magnitude, but what some numbers are, and these vary for what some radars are. Here are some numbers for, I picked, that's a reasonable one for a radar. You can have a peak power as much as a megawatt, more, less, often. Pulse lengths, you could say plus or minus 1 or 2 orders of magnitude or something like that. 100 microseconds, you could have a microsecond. But the target return, I want to just point out, is very small. It can be as little as a microwatt of power. And so after you turn your transmitter on, you want to make sure that none of that transmitter leaks into your receiver while you have your receiver turned on. Important thing. And a kilohertz, a millisecond between pulses, is a number. Numbers go as high as 100 kilohertz, 10 kilohertz, 1 kilohertz, several hundred hertz. But those are the orders of magnitude of the pulse repetition of, actually I was giving you the pulse repetition frequencies. You could get, say, a hundredth of a second up to microseconds, fractions of a microsecond, which would correspond to pulse repetition intervals of, as I go through my mind, easily I can think of radars that operate at 500 or 600 hertz, and also radars that operate, and we'll see later why, that operate at 80 or 90,000 hertz. And the average power for this particular example is 100 kilowatts because we're running the transmitter at a duty cycle of 10%. Sometimes it's 0.1%, and sometimes it's 15-20%. It can go over those kinds of ranges. And that's just to give you an idea of the general orders of magnitude with big errors that these numbers can be. Now, what does a radar observe? What does a radar observe in terms of numbers? I went over some of this before. We obviously know we transmit out, and this is the signal underneath that square envelope of an ideal transmitted signal just for one pulse, and we get back. The transmitted signal goes out, reflects off the target, which I'm going to assume is going at a constant velocity v, and that's the velocity in the direction of the radar. Note that. It's not going across at another. I'll get into that issue a little later. But for this particular example, it's going in a direction v towards the radar. Everything's along a line. And there'll be a received signal, the echo off the target, we scatter back and go into the radar. The form of the transmitted signal is just this. It's an amplitude as a function of time, and that would contain the information saying there was no signal before this time. And then we got this exponential complex signal. This is obviously one of the real or imaginary component. And it's on for a while, and then contained in the A of t would be that it's zero afterwards. And then what do we receive? Well, we don't receive the full signal back. It's attenuated. It's delayed in time because it takes time to go out and back. The delay time is tau, so you have to subtract that off. And then there's this other. The frequency of this signal we transmitted, has changed. And that is due to a principle called the Doppler effect. I'm going to note up here that the range to the radar of the target is just its range at t equals 0. And since it's coming this way, you have to subtract off the velocity times the time because the target's moving. But I want to point out that the received signal's frequency is changed because of a physical effect known as the Doppler effect. And I'm going to go over with you a derivation of the Doppler effect in a view graph or so. So we're going to be able to measure the amplitude of the target, which depends on the radar cross-section. We're going to have a whole lecture on that. Just take it my word. The parameters of the radar, how powerful it was, the range, how far away you were. We're going to have directionality from the antenna. The beam width of the antenna is going to be relatively narrow, hopefully, so that we'll be able to measure azimuth and elevation to certain accuracies. And we'll measure this time delay, which will implicitly give us, at a given time, the range that the radar is away. This is the, and then we have the Doppler frequency, which is twice the velocity, and that's the velocity along the line of sight of the radar, accurately. In this case, since it's all along the line, it's the velocity of the aircraft, times the frequency divided by the speed of light, which from electromagnetism, the frequency divided by the speed of light is the wavelength. So the Doppler shift is twice the velocity, the radio velocity divided by the wavelength of the radiation that you transmit. Okay. Now let's derive the Doppler shift, and again we'll derive it for a linear target, but it should be noted that the Doppler shift only depends on the radial component of velocity. Okay? Okay, this peak right here, I denote A, and one wavelength later I denote the peak B. And that peak A leaves at time t equals 0 when the radar is at R0. And the time it arrives at is a delta time later, a little bit later. And we have the aircraft moving with a radial velocity v. And if it were moving at say rising, the radial velocity would be less than the velocity along the line of sight of the target and the radar. But let's just assume that the radial velocity is along the line of sight of the full velocity vector of the target. The period of the transmitted pulse is obviously the time between the peaks, and the frequency of the radiation is 1 over that. So we have these relations which are straightforward. And we note that C times the change in, is going to be the relationship between the distance of the target at this point, an arbitrary, after it's moved into delta t, will be C delta t, which is R0 minus the velocity times delta t, or that delta t is this R0, the total length divided by the speed of light plus that radial velocity. From this relation, one can see easily that the time when peak A arrives at is 2R0 over that speed. The time when peak B arrives is 2, and a different distance because the target has moved a distance. So that distance is it's not R0 but R0 minus VT divided by the speed. Okay? Now let's move to the next. Now the period of the transmitted signal is T, and the received signal period is just the time between the received peaks. And then we just looked at what the frequency was. This is the time it received peak A and B. And that difference in time, the period, is this. Its frequency is 1 over that, which leads us, with a little algebra, to the frequency of the received signal is F0 1 plus V over C divided by 1 minus V over C. Well, then we realize that the speed of light is 186,000 miles a second, 3 times 10 to the 8th meters per second, very big number. To put this in perspective, the speed of light is much larger than any velocity of a target we're going to deal with, like 100 miles an hour versus 186,000 miles a second. So we can approximate V as being very much smaller than C, and then this bottom denominator can be approximated by this power series. And when you do that, then the frequency that you receive is the carrier frequency that you transmitted plus 2V over C divided by the carrier frequency, which through simple manipulation of C over the carrier frequency is lambda. We get that the Doppler shift is plus 2V over lambda. And that was for an approaching target. For a target that was receding, we have a negative sign. And the gentleman who figured this all out was Christian Andreas Doppler. And here's a picture of the gentleman. So we see, here is the derivation of not the derivation, but the statement of the Doppler frequency, noting that this radial velocity, it's the radial velocity that counts, and this shift in frequency is positive for approaching targets and will be negative. There'll be a smaller frequency for receding targets. Okay, now I believe that is the end of this lecture, piece of this lecture.